In this instructional video, we're going to be working with some Ka values, those acid dissociation constants for weak acids. So let's look at our first problem. We're going to write the chemical equation and the Ka expression for the ionization of each of the following acids in aqueous solution. So we have HBrO2, an acid. We know that. We said it's going to be in an aqueous solution, so we can add H2O. So we have our acid, we have our base. And we're going to be in dynamic equilibrium here with, let's think of our Bronsted-Lowry conjugate acid and base. Our acid is going to dissociate. So we're going to have our H is going to join with our water to form hydronium ion. I guess we need to do this here. And we drop our hydrogen here, so we have our BrO2 minus. So we have our conjugate acid and our conjugate base on the right. All right, and then let's write our chemical equation here. And then, of course, for our Ka, we do our products over reactant with the water, of course, dropping out, or the dissociated over the molecular. So we're going to have the concentration of our H3O plus, or we can just say our H plus. Remember, they're used interchangeably, so our conjugate acid times the concentration of our conjugate base all over the molecular form of our acid, HBrO2. All right, good work. Let's move on to the next one. All right, and here we have HC3H5O2. And again, we're putting it in an aqueous solution, so let's set this up. In water. And we're going to have our proton transfer. So we have our acid, we have our base, we have our Bronsted-Lowry conjugate acid, conjugate base formed. We know that this H proton transfer is going to make H3O plus, so our conjugate acid, and our conjugate base, which is just going to be our acid with one less hydrogen, C3H5O2 minus. All right, and then to set up our Ka for this expression, our Ka is equal to our products over our reactant, of course, with water dropping out. So our H3O plus times our C3H5O conjugate base all over the molecular form of our acid, HC3H5O2. So hopefully this is a review from last chapter. The only difference being that we're putting this into an expression to find our Ka, our constant for weak acids. Let's look at another example here. We've got lactic acid. It only has one acidic hydrogen, so it's monoprotic. So you know the solution, HC3H5O3, when placed in water, is going to dissociate and form a dynamic equilibrium with H3O, forming H3O plus. And so this is our conjugate acid. I don't need to write that. And our conjugate base, so losing that acidic hydrogen, so C3H5O3 minus. So we have a 0.1 molar solution of lactic acid. So our initial is 0.1 molar. And it has a pH of 2.44. Calculate the Ka. So we know that this 2.44 is coming from my H plus, or my hydronium, at equilibrium. So we know that initially I also have 0 concentration of my products. So let's find this change. Let's find the equilibrium. But first, let's change our pH into concentration. We know that pH is equal to the negative log of our H plus, or H3O plus. And we also know that we can go the other way. We can flip-flop this. If we do 10 to the negative pH, we can get our H plus concentration at equilibrium. So let's plug this into our calculator. So when I do 10 to the negative 2.44, I get an H plus concentration down here. Let's form some lines. So 10 to the negative 2.44 is equal to 0.00363 molarity. And we also know that because of our stoichiometric ratios, we have a 1-to-1 ratio here. That's also the concentration of my conjugate base. And that also tells me that in order to go from 0 to 0.00363, I had to add 0.00363 to get there. And because of that, we know that this is also a 1-to-1 ratio. So while I gained this much, I also lost that much of my initial reactant. So I'm minus 0.00363 m. So let's figure out what our original acid is at equilibrium. So 0.1 minus 0.00363. And we can see at equilibrium, here is my concentration. So 0.09637. Okay, and now we can find our Ka now that we know all of our concentration values at equilibrium. It's just products over reactant, right? And remember, we can just cross off our H2O. That just drops right out of the equation. So let's plug that in and do our Ka is equal to our products over reactants. So we can even write here our H3O plus times our C3H5O3 minus. So our dissociated over our non-dissociated, or over the molecular form of the acid, HC3H5O3. Okay, so this is going to be equal to 0.00363 times 0.00363. So we could just simplify that and say 0.00363 squared over the concentration over here, 0.09637. And let's do some calculator work. 0.00363 squared divided by 0.09637. And I got a Ka value of 1.37 times 10 to the negative fourth. Here is our Ka value. Let's look at our next problem here. We have 0.1 molar solution of chloroacetic acid. So let's just start off writing it. Our expression here, ClCH2COOH. And here we have our Cu. This is our organic acid. And assuming that we're placing it in water here and it's setting up an equilibrium, this H here, this is our acidic hydrogen that will be plucked off. So we're going to have our conjugate base pair over here, our Cl, CH2, COO minus. And again, that's the proton that is leaving, and it is going to be forming our H3O plus. All right, so now let's look at our ice table here. We can cross off water. And it tells us that we're initially starting with a 0.1 molar solution of this acid, 0.1 molar. And we're also assuming that this reaction hasn't started yet. So I have no products at this point. Now it's telling us that at equilibrium, 11% is ionized. So let's take what we started with, our 0.1, and times that by 0.11. And we see here that at equilibrium, we have 0.011 molar of my hydronium, my conjugate acid, my conjugate base. And again, remember, we could go back and double check that. Remember, to find percent ionization, we took our H plus value and divided it by what we originally started with. So if I were to just back this up and double check our work, 0.011 divided by 0.1, and then we would times it by 100, and we get 11%. So we know our our equilibrium concentrations here. So that means that to go from 0 to 0.011, we had to add 0.011. And therefore, because of the stoichiometric ratio, everything being 1 to 1, I had to lose, because this is my reactant, I'm going to lose reactant while I'm gaining product. So I'm going to lose 0.011 on the left. Now we just need to do some math here and do 0.1 minus 0.011 to get our equilibrium concentration of our chloroacetic acid of 0.089. And now we have everything we need to find the Ka for this acid, because we know we're going to do products over reactants to find our Ka expression. And we're doing 0.011 times 0.011. So if I could just simplify and say 0.011 squared over the concentration of my reactant, 0.089. So now let's plug this into our calculator. We'll do 0.011 squared divided by 0.089. And I get 0.0014 for my Ka. And again, no units for Ka. Okay, let's look at our next problem. We have a particular sample of vinegar that has a pH of 2.90. Notice that our pH, the common accepted value, that we go to 2 decimal places. Assuming that acetic acid is the only acid that vinegar contains, and we're given the Ka, calculate the concentration of acetic acid in vinegar. Okay, so let's write out what we know. Acetic acid, if you weren't sure of its chemical equation, we could look at our Appendix D, and we could find acetic acid is HC2H3O2. And there's its Ka value that was given to us in the problem. So here we know it's HC2H3O2. And again, we're putting it in water to form a dynamic equilibrium. This is our acidic hydrogen that will be leaving. So we've got C2H3O2 minus plus H3O plus. Okay, let's set up our ice table so we can write down everything that we know. Okay. So we know the pH is 2.90. We also know that that is a value of, if I do 10 to the negative pH, that I can get my H plus concentration. So if I do 10 to the negative 2.90, let's see what I get here. I get 0.001259. So that's the 0.001259 molarity. That's the concentration for my H3O plus. I also know that because of 1-to-1 stoichiometric ratio, that's the concentration for my conjugate base. So let's write these two in, 0.001259 molarity. I also know that I'm starting with a certain concentration of acetic acid, but I don't know what that is. We'll just call that X. I also know that I'm initially starting with that amount, and I don't have any of my products yet, assuming that the reaction has not started. So knowing all of that information, what can I fill in on my table? Well, I know in order to go from 0 to 0.001259, I had to add 0.001259. And I also had to do the same thing for my H3O plus, because they're 1-to-1, so plus 0.001259. I also know that, even though I don't know how much I started with, all because of stoichiometric ratio, my reactant had to lose that much in order to form that product. So we had to lose 0.001259. So therefore, at equilibrium, this value would be X minus 0.001259. So now, my only missing variable is X, and I know my Ka. So I can plug this all into my equilibrium expression constant for my weak acid by doing products over reactant and setting it equal to 1.8 times 10 to the negative fifth and solving for X. When I solve for X, that will give me my initial concentration. So let's do some calculator work here. Our Ka, which is 1.8 times 10 to the negative fifth, is equal to our products. So this times this is equal to this squared. So let's do 0.001259 squared over my reactants, which is X minus 0.001259. So let's simplify this, and we're going to cross multiply. So I will have 1.85 times 10 to the negative fifth times X minus 0.001259 equal to 0.001259 squared. Let's just do this, take our answer and square it. So we would have 1.585 times 10 to the negative fourth. Oh, I'm sorry, negative 6. 1.585 times 10 to the negative 6. Well, first of all, I just went back to look to distribute this, and I'm wondering where the heck I got 1.85. It shouldn't be. It should just be 1.8. So I don't know where that 5 came from. Let's just scribble that out. So I'm going to have 1.5 times 10 to the fifth times x to give me 1.8 times 10 to the negative fifth x. And then we're going to distribute that 1.8 times 10 to the negative fifth times, not multiply, or not minus, times 0.001259, and then we get 2.2662 times 10 to the eighth. So we're subtracting that. 2.2662 times 10 to the eighth, negative eighth, is equal to 1.585 times 10 to the negative 6. All right, let's do some more simplifying. So next we need to simplify. We need to add 2.2662 times 10 to the 8th to both sides. So that will leave us with 1.8 times 10 to the negative 5th is equal to, so I've got my 1.585 times 10 to the negative 6 plus 2.2662 times 10 to the negative 8. I'm going to add those, and I have 1.607. We'll just write the whole thing out. 662 times 10 to the negative 6. And then in order to get x by itself, we need to divide both sides by 1.8 times 10 to the negative 5th to get x by itself. So divide that answer, 1.8 times 10 to the negative 5th. And I should get x equals 0.089. And actually, I might just go one more unit here because our pH was given in 3 sig figs. So 0.0893 molar is the concentration for our original acetic acid. So that's our concentration for HC2H3O2. So looking back at this problem, making sure everybody understands where we were at, we were given pH, and pH we were able to take 10 to the negative pH to get our ion concentrations at equilibrium. Knowing this, we were able to find that change row where we knew we started with 0 initial, and we found that change, which allowed us to figure out the change that we were lost in by our acetic acid. So that was denoted as our X. So X minus that change. We're then able to plug that into our equilibrium expression because we knew Ka. So then we just let algebra do the work. We're able to find that original X concentration of acetic acid. Let's keep working. Let's look at this one. The acid dissociation constant of benzoic acid, which is HC7H5O2. is 6.3 times 10 to the negative 5th. Calculate equilibrium concentrations. Well, first, let's write out our equilibrium. So we know that we're adding this in with water and that we're going to lose our acidic hydrogen here. So we've got our H3O plus and our C7H5O2 minus. All right, and we know that the initial concentration of this benzoic acid is 0.05 molar. So let's write out our ice chart. So this is 0.05 molar. And again, we cross out our water. We initially don't have any of our ions formed yet because it hasn't started dissociation yet at the initial point. We know that because it's a 1-to-1 stoichiometric ratio, we're going to lose X, a certain amount. We're going to gain a certain amount over here with my products. So my change in equilibrium would be 0.05 minus X. And over here we've got X. All right. We're given our Ka value of 6.3 times 10 to the negative 5th. So we know that 6.3 times 10 to the negative 5th is equal to our products over our reactants. So if I were to do X times X, we get X squared. Over our reactant at equilibrium, 0.05 minus X. So let's write this out and do some algebra here. We would have X squared is equal to 6.3 times 10 to the negative 5th times 0.05 minus X. And we'll need to do some distributing here because we're going to have to use the quadratic formula. So when we distribute and we subtract X squared from both sides, we would have 0 is equal to negative x squared, right, because we're subtracting x, minus 6.3 times 10 to the negative 5th x, plus 3.15 times 10 to the negative 6. So when we plug into our quadratic formula on our calculators here, we have got A is equal to negative 1. Here we've got negative 1. B, we've got negative 6.3 times 10 to the negative 5th. And C is 3.15 times 10 to the negative 6. So here I wrote down our ABCs here. When we plug this in, we get two different numbers, and obviously we can't have a negative number. So our x is going to be equal to 0.001744, which we know that this x value is our concentration for our H3O+. So let's write this down. 0.001744 for our H3O+, same with our C7H5O2 minus, so that is our initial concentration for H3O+. This is a misprint here. Our C7H5O2, this should be a lower 2 with a -1 charge. So we've got that here. And then we need to find our concentration for our benzoic acid. So we need to plug that we need to plug that X into here. So we're going to do our 0.05 minus that X. 0.05 minus 0.001744. And our concentration for our benzoic acid would be 0.04826. 0.04826. And that takes care of all of our equilibrium concentrations. And again, looking back at this, we were given our initial concentration of benzoic acid, and initially we did not have any products. So we lost a certain amount of our benzoic acid, and we gained that same amount for our products. So we had to plug this into our equilibrium constant. So we knew X, we knew 0.05 minus X. We were given Ka. We could have also looked on our Appendix D to find benzoic acid's Ka. And we only had one ionizing proton, so there will only be a Ka1. So 6.3 times 10 to the 5th is equal to X times X is X squared over 0.05 minus X. We then simplified. We did 6.3 times 10 to the negative 5th times 0.05 minus X equal to X squared. We distributed 6.3 times 10 to the negative 5th times 0.05, and we got 3.15 times 10 to the negative 6. We minused, because of our minus, we're minus 6.3 times 10 to the negative 5th X. And then we subtracted X squared from both sides to get negative X squared on the left, all equal to 0. So we do our A, our B, and our C. One of the X's doesn't make sense. We can't have a negative concentration. So we found our X, which is the concentration of our hydronium and our conjugate base. And then plugged our X into here and did 0.05 minus X to find our equilibrium concentration of benzoic acid.